Ever wondered why a microwave heats food so fast? In the next few minutes, we'll uncover how invisible waves turn kitchen staples into steaming delights. Microwaves are a form of electromagnetic radiation that falls between infrared and radio waves. In household ovens, they serve as the primary heating source because they can penetrate food quickly. The core component is the magnetron, which converts electrical energy into microwave photons. These photons travel through a waveguide toward the cooking cavity where they are reflected. Inside the cavity, standing waves form, creating hot spots that vibrate water molecules. The vibration generates heat by friction, raising the temperature of the food uniformly. A turntable rotates the dish so that all parts experience similar exposure to the waves. The oven's metal walls act as a Faraday cage, containing the microwaves safely inside. When the magnetron stops, the cavity cools and any remaining photons are absorbed by the walls. This mechanism allows for rapid heating without burning the surface of the food. Pause 0.8. Electromagnetic waves travel through space as oscillating electric and magnetic fields. They vary in wavelength, from long radio waves to short gamma rays. The entire range is called the electromagnetic spectrum. Microwaves occupy a middle portion of this spectrum. Their wavelengths are roughly between 1 millimeter and 1 meter. In everyday life, we use microwaves at about 2.45 gigahertz. This frequency is chosen because it excites water molecules efficiently. When a microwave oven emits these waves, the fields oscillate rapidly. Water molecules absorb this energy and rotate faster, generating heat. The heat spreads through conduction to cook the food evenly. Thus, microwaves use electromagnetic radiation to warm food without burning it. Understanding where microwaves sit in the spectrum helps explain their unique heating power. Pause 0.8. The magnetron is the heart that turns electricity into microwaves. Inside, a high-voltage supply creates a strong electric field across a cavity. Electrons are emitted from a heated cathode and accelerated by this field. As they move, a magnetic field forces them to spiral in a circular path. The spiraling motion produces oscillating currents that generate electromagnetic waves. These waves resonate at 2.45 gigahertz, the frequency chosen for food heating efficiency. The cavity walls reflect the waves back toward the center, amplifying their strength. When the microwaves exit through a small aperture, they enter the cooking chamber. The radiation penetrates food and agitates water molecules, producing heat. Thus, the magnetron converts electrical energy into focused microwave power that cooks quickly. This process is safe because the waves are contained. Pause 0.8. Microwaves are electromagnetic waves that oscillate at frequencies around 2.45 gigahertz. When they enter food, the waves travel through it rapidly and uniformly. Water molecules inside possess a permanent dipole moment due to their polar structure. The alternating electric field forces each dipole to flip back and forth in sync with the wave. This rapid flipping generates friction between neighboring molecules as they collide. Frictional interactions convert mechanical motion into thermal energy, raising temperature. Heat rises uniformly throughout the food, warming every part simultaneously. Microwaves penetrate deeply before being absorbed, allowing efficient heating of thick items. No external heater is required. The food itself becomes the source of heat. Dipole rotation explains why microwaves cook faster than conventional ovens that rely on conduction. Understanding this mechanism helps engineers design safer, more energy-efficient appliances. The rapid energy transfer occurs in microseconds, making microwave cooking highly efficient. Pause 0.8. Inside a microwave oven, electromagnetic waves bounce off the metal walls and travel through the food. Each wavefront moves at about 300,000 kilometers per second, but only a tiny fraction of that energy is absorbed by the food. When two waves meet, they interfere either reinforcing each other or canceling out creating a pattern of peaks and troughs. The peaks are called hot spots. Here the electric field is strongest and molecules vibrate most vigorously. The troughs become cold zones where less energy reaches, so those areas heat more slowly. Because the waves reflect repeatedly, they form standing waves that persist until the food's temperature rises enough to dampen them. The standing wave pattern explains why some parts of a pizza slice are sizzling, while others remain cool. The microwave's rotating turntable helps spread the energy by moving the food relative to the fixed hotspots. As molecules absorb the alternating electric field, they generate heat through dielectric heating. The Euros essentially friction at the molecular level. A 3A circumflex Euros D simulation can overlay a temperature map onto the wave fronts, visually showing where heat concentrates and where it lags. Pause 0.8. Microwave ovens use electromagnetic waves to agitate water molecules, creating heat that cooks the food. When metal is placed inside, it reflects those waves and can spark or damage the cavity. The turntable rotates the dish so every part receives equal exposure to the waves. Uneven heating would leave cold spots, but rotation ensures a uniform temperature throughout. Containers made of glass or ceramic are safe because they do not interfere with the waves. Plastic containers should be microwave safe, otherwise, chemicals can leach into the food. If a container is too small, steam builds up and may cause pressure to rise. A vented or loosely covered dish allows steam to escape, preventing splatter and burns. Always check the manufacturer's guidelines. Some foods need a specific type of container. By avoiding metal, using proper containers, and letting the turntable do its job, you keep microwaves safe. Remember that a well-maintained oven will deliver consistent heating without risking damage or injury. Pause 0.8. Microwaves at 2.45A circumflex Euros gigahertz excite water molecules via dipole rotation, converting energy into heat. Magnetrons produce these waves from electrical input. Inside the oven, reflected waves form standing patterns that can cause hot spots, while turntables help distribute heat more evenly.